Okay, good afternoon, everybody, and welcome to the second Lumer Lecture of our cost action mSPACE. So today I'm here on behalf of Working Group 2, and we're delighted to have with us Marco Marletta, who is a member of our action, a member of our working group, but also a leading expert on a number of topics that are very much in the list of topics we want to study in our working group in this action. So Marco obtained his doctorate 35 years ago, as we were discussing, from the Royal Military College of Sciences in the UK, on a relatively applied or somewhere very much straddling the boundary between applied and pure mathematics. He was then a lecturer in Leicester and has been in Cardiff for the last 25 years, where he's held a chair in analysis for 20. And he, as I mentioned, is an expert in basically at the intersection of PDEs, operator theory, and with applications to mathematical physics and such, in particular spectral theory. In particular, he works on topics like non-self-adjoint operators, what can you say about the spectrum? He is interested in Dirichlet-Neumann operators. So, what's happening at the boundary? What can I say about the Laplacian based on looking at Dirichlet-Neumann data, that sort of thing. Things that we are all very much interested in. And today he will be talking about, basically something chosen from those topics, something operator theoretic, which will, according to the title at least, and I'm very much confident it will, have applications to PDEs, namely numerical range or essential numerical range of operators and operator pencils. So thank you very much again, Marco, for being with us, and the metaphorical floor is yours.
So thank you very much, James, for that very flattering introduction. I hope you can all see me. So I can't see you, unfortunately, the way that this system works. When I'm talking to the slides, I can only see the slides. But yeah, if people have questions, then please shout, because I can't see you. I can't see even what's in the chat. So I hope the topic's not going to be too elementary in parts. I was given a stern warning that I should keep the talk at a level where it would be accessible to a wide audience, and that's what I've tried to do. So as few technical details as possible, and then I can try to go into things in greater detail if you ask. And I have a blackboard set up here with a camera pointing at it, which I'll switch to if necessary. I guess I'd better start by not assuming that people know what a numerical range is, even though this is a Lumer lecture, and Lumer certainly did know what a numerical range was. I'm not going to assume that you know what a numerical range is. So we start with some operator T on a domain in a Hilbert space. There's no assumption that T is bounded. We're not even assuming at this stage that T is closed or closable. And the numerical range of T, typically denoted by W for reasons I'm not entirely sure, is a set in the complex plane. So what you do is you look at all the inner products of Tx with X as X ranges over the intersection between the domain of T and the unit sphere. Okay, so that's what the numerical range of T is. So it turns out that this is a convex set. That's not, it's not obvious that this is a convex set, but it is a convex set in the complex plane. The proof of this fact is not particularly inspiring, so I shan't do it. But it's easy enough, just not very beautiful. And the closure of this numerical range contains the approximate point spectrum of T.
Sorry to interrupt. We've got a comment that somebody can't see the slides. I can see the slides. I'm not sure if other people are having that problem. Apologies again for the interruption.
I see them.
I see them too.
Does anyone else have this problem?
Before, at the beginning, before the introduction, and then they were gone. So, I don't know.
I mean,
That which might be related.
Resharing. I can try unsharing and resharing if that might help. Let's try unsharing and resharing.
Yeah.
So I'll try stop share and restart the share. So
yeah, now I see. Yes.
Okay, I can see them too. Again, sorry for the interruption. Please keep going.
Yeah, that's better. Yeah. So right, so the closure of the numerical range contains it's convex, so it contains therefore also the convex hull of this set. It contains something called the approximate point spectrum of T. Now, that in particular means it contains all the eigenvalues of T if there are any. It contains the sigma E2 essential spectrum of T for those of you who know the taxonomy from the book of Edmonds and Evans. You have to be a little bit careful here. So I can give you an example where this isn't true. If you take the Laplacian on any nice bounded domain in RD and simultaneously impose both homogeneous Dirichlet and homogeneous Neumann boundary conditions, okay, which is far too many, of course, then the operator T that you get by doing that is symmetric, but it's not self-adjoint. So it's not self-adjoint because you've got too many boundary conditions. You can never solve the resulting operator equation. So what happens in that case is that the spectrum of that T with a Laplacian with too many boundary conditions is the whole complex plane. Okay, but then it's a very easy integration by parts calculation to show that the numerical range, on the other hand, is the positive semi-axis. Okay, so you've got to be careful not to do bonkers things that mean that your operator has no points in its resolvent set. So the hypothesis for this to be for you to get this result, that the closure of the numerical range contains the spectrum and therefore also its convex hull, is that each is the resolvent set of T has to be non-empty, and in each component, in each connected component of the resolvent set, that they're so each connected component of the resolvent set has to contain a point that's not in the numerical range of T. So there are technical hypotheses you need in order to make this be true, but it's true for all reasonable cases that you might want to do in applications. So we'll be assuming in this talk that this is true, and so in particular, a very crude estimate of where the spectrum of T might lie would be to say, well, it lies inside the closure of the numerical range of T, always assuming that you can calculate this numerical range somehow. If T is normal, then this inclusion becomes an equality. So in particular, if T is unitary or self-adjoint, this inclusion is an equality. And then the other much easier bound is that if T is bounded, then just by using whatever Cauchy-Schwarz, you can see that the numerical range of T is contained in the closed unit disk in a complex plane with center 0 and radius norm of T. Now, there's also bounds in the resolvent in terms of distance to the numerical range. So if you've got an operator T whose numerical range is whose resolvent is non-empty and which satisfies the hypotheses that we mentioned before, then the norm of the resolvent is bounded by 1 over the distance to the numerical range. In the self-adjoint case, you can replace this, of course, by distance to the spectrum. Okay, so this is the best that you can do if you're not normal or not self-adjoint. You get distance to the numerical range instead of distance to the spectrum. And then I'm very conscious of the fact that this is going to be a result that's very well known to all the people in the semigroup community in mSPACE. So you can bound the semigroup associated with T, if T is m sectorial, by this exponential function here, and the coefficient here that appears is the infimum of the real part of elements of the numerical range of T. Now, there's one other thing about numerical range that you become quickly aware of if you go to something like one of the Iwata conferences. So at the Iwata conferences, numerical ranges are now big business, and the parallel sessions on numerical ranges are some of the most popular. Typically, you'd have 60 talks at Iwata on numerical ranges, and there are lots of people working on variations on the Crouzet conjecture and other related conjectures. So this is a very simple conjecture to state, which is that if you take any square matrix, so we're not even talking about operators here, we're talking about matrices. You take any square matrix and any polynomial, then the norm of P of T is bounded by a multiple of this thing here, the supremum over Z in the numerical range of T of mod P of Z. And the deal with the Crouzet conjecture is what's the constant. So that the conjecture is that C equals 2 should be possible. At the moment, this is proved for normal matrices. And for other matrices, it's proved with C is 1 plus root 2. And Crouzet's original 2007 paper had C as 11.08. I believe even in the 3x3 case, the case of 3x3 matrices, it's not proved that you can do C as 2 here. Of course, the numerical evidence is all there to support this, but currently 1 plus root 2, so what's that, about 2.4, is the best that anyone has managed to prove. I'm not aware that this conjecture has any particular applications, but yeah, it's been around here now for the thick end of 20 years, so it has real pedigree. Okay, so here's a couple of pictures of numerical ranges. Here are a couple of matrices. So you're going to have to ignore the multicolors in the pictures. Just think of these as being uniformly colored. The colors are an artifact of the package I used for plotting these sets. So here are two matrices. This one here you can see is non-normal. Okay, so non-self-adjoint matrix. But with real eigenvalues, by the way, 1 and 2. And the numerical range is this elliptical region in the complex plane. The center, I'm not quite sure where the center is. I could probably work it out, but it looks as if it's at about 1.5 on the real axis. And I don't know where well, okay, you can kind of see where one of the foci of the ellipse is. Over here, on the other hand, so this is a numerical range of T1 here. Now, T2, if you look at this matrix T2, it's diagonal. Its eigenvalues are strictly complex. And because it's diagonal, it's normal. And so its numerical range, it turns out, then is the convex hull of the eigenvalues. And the convex hull of 3 points is just a triangle. So in general, if you've got a normal matrix, then the numerical range is a polygon whose vertices are the eigenvalues. Pardon me. And the other thing that's proved in the case when T is bounded but not necessarily a matrix is that any corner of the boundary of the numerical range has to lie in the spectrum of the operator. Okay, so that's a calculation that exploits the fact that if you're at a corner, then you don't have a uniquely defined tangent direction. Now, for matrices, calculating numerical ranges is relatively easy. There's an algorithm going back to 1973 by two fairly well-known numerical linear algebra people, Horn and Johnson. And the way that it works is essentially you rotate the matrix, and well, you don't rotate. Well, you rotate the matrix so there's your t. You rotate it by an angle theta. You take the real part, and you calculate its biggest eigenvalue, and then you multiply that by e to the minus I theta. So by doing this, you're rotating this set here around so that the point you're trying to calculate is always rotated to lie here on the rightmost boundary, and that's what you're calculating using some suitable numerical linear algebra package. For other types of operator, who knows? Matt Colebrook in Cambridge has results on the complexity of calculating numerical ranges, and in general, it's expected from a computational point of view to be harder maybe than calculating spectrum. So let's do some examples. So we saw some matrix examples on the last slide. Let's do some differential operator examples. So if you take second derivative, minus second derivative in one dimension, then of course the spectrum is the positive semi-axis, including 0. The numerical range is actually, for this, it's an open set. It doesn't include 0. So you do have to take its closure in order to make sure that you capture the whole spectrum. So the reason that 0 is not in here is because 0 is not an eigenvalue of that operator. If you look at the same operator on a compact interval with Dirichlet boundary conditions, then of course you're going to have a discrete spectrum, unbounded above, and then the numerical range is the convex hull of that spectrum. So it starts in this case at pi squared and goes up to infinity. And in this case, pi squared, the bottom of the spectrum, is indeed an eigenvalue, and so that is already in the numerical range without you having to worry about taking closures. So then I mentioned this earlier, if you take the same operator, but then impose an extra boundary condition, so there's one extra boundary condition, you've now got too many boundary conditions, the spectrum of this operator is now the whole complex plane because you've got too many boundary conditions. It's not entirely obvious that the numerical range is this open half line, but it is. So you can prove that that's what the numerical range looks like. So far, these have all been quite tame examples. I'm going to show you some hopefully more interesting examples later in the talk. These examples are designed to somehow get your feeling for what numerical ranges are. So another case where you might think about numerical ranges, and this is perhaps not a good example to apply numerical ranges, is the case of Koopman operators. So Koopman operators, for those of you who haven't seen them before, are like generalizations of shift operators. So they could be the time advance map associated with some dynamical system, except that, yeah, so the operator that maps a function to its value at some point that's the shift of the original point by the time advance map. So the kind of canonical Koopman operator is unilateral shift in little L2 of Z. Of course, this operator has norm 1. So then we know its numerical range is contained in the closed unit disk. We also know that this is wrong. So this should say the spectrum of T is the unit circle. Okay, so the spectrum of the unilateral shift is the unit circle. And then because we know that the numerical range is got to contain the convex hull of this spectrum, the closed numerical range has to be the closed unit disk, right? So the closed numerical range has to has to contain the closed unit disk, and it has to be contained in the closed unit disk. So it is actually the closed unit disk. So this is true. But what about if you take away the closure? So is the numerical range itself closed for this example? And the answer is no. One of the things I discovered about Lumer when I was looking at the Wikipedia page on Lumer before giving this talk is that he worked with Halmosh. And in fact, if you look on Halmosh's book of problems, you'll see that problem 212 is to show that if you have points in the numerical range whose modulus is equal to the norm of the operator, then these points are always eigenvalues. Okay, now the unilateral shift doesn't have any eigenvalues in L2 of Z. And so for this case, the numerical range is actually the open unit disk. Okay, so now let me get on to the topic of the talk, which is essential numerical range. So what you do for essential numerical range is instead of taking just a single inner product of Tx with X, you take the limit of inner products Txk with Xk, where you choose the sequence Xk in the domain of T to be a unit sequence that's tending to zero weakly. So the way I've written the definition here is the way it was originally written in 1968 by Stampley and Williams. And this is the definition for bounded T. Okay, I say it's the definition. They actually, they and other people gave 5 different definitions of this concept that all turn out to be equivalent to this one. So this is a closed convex set, and it contains the convex hull of the E2 essential spectrum. And again, for T bounded and normal, this inclusion becomes an equality. So the essential numerical range is then the convex hull of the essential spectrum. So here are some of the equivalent characterizations for the case of bounded T. So you could take the numerical range of T plus K, where K is compact, take its closure, and then intersect over all compact operators K. That would give you the same result. You could take a finite rank bounded operator K, do the corresponding thing, and again, you'd get back to the same set. And then you can also restrict the operator to the orthogonal, well, basically to spaces of finite codimension, take their numerical ranges, close them, intersect over all spaces of finite codimension, and you will again get the essential numerical range of T. And the fact that these are all equivalent really depends very heavily on the fact that T is bounded. And so the question number 1 is, what can we say then about unbounded T's? And if we do manage to say something, if we manage to choose one of these, will it be equivalent to all the others? And I guess the third question is, why do we care anyway? Okay, so the definition that we're going to choose, so this is in a paper I wrote with Sabine Boegli and Christiane Tretter in JFA in 2020, is that basically we just take the definition, the first definition I showed you from the bounded case, and restrict the x's to lie in the domain of T, which is about the minimum perturbation that you could make and have the thing still make sense. Okay, so good. This thing still makes sense. It turns out it's still a convex set. It's still closed. But there are now some radical differences. So let's suppose we now consider this diagonal operator in L2 of Z, which is a diagonal operator whose entries are just the non-zero integers. So this is a self-adjoint operator. It's got compact resolvent. Its essential spectrum is therefore empty. Okay. However, it's pretty easy to show that any point on the whole real axis is in the essential numerical range of this T. That's, I mean, you just take an xn that's a linear combination of the E minus n and the E plus n standard basis vectors, adjust the coefficients in the linear combination to get norm 1, and yeah, you can pretty much make this converge to anything you like. So you get the essential numerical range is now no longer the convex hull of the essential spectrum because the essential spectrum is now empty. And instead, what you see here is a set that in 2004, Levitin and Szargorodzki called the extended essential spectrum of T. The difference now, of course, is that our definition here makes sense for operators that are not necessarily self-adjoint, whereas the definition of extended essential spectrum in Levitin-Szargorodzki was based on the assumption that T was self-adjoint. Okay, so we'll have now a quick quiz about proper relationship between the numerical range and the essential numerical range. So, geometric properties. Number one, let's suppose the numerical range of T is a line. So by line, I mean something that goes to infinity in two directions. Okay, so not a ray. A ray goes to infinity in one direction. WT is the numerical range is a line, then the essential numerical range is also the same line. Okay, so in that case, the essential numerical range doesn't give you any extra information that the numerical range didn't give you. And that covers, by the way, the example on the previous slide. For example, in the previous slide, the numerical range was a whole real line, and so it shouldn't have been a surprise if we had this theorem that the essential numerical range is also the same whole real line. Okay. Now let's think, what if the essential numerical range is a strip? Okay, sorry, what is a numerical range is a strip. So it doesn't have to be a horizontal strip. It's just some straight strip in the complex plane of some fixed width going to infinity in two directions. What can we say? So at this point, we probably think, well, I guess a strip is a union of lines, and so maybe the essential numerical range is also going to be a strip. Well, actually, it could also be a line. So you can get a collapse happening, and you can get a case where this is a strip, but that's a line. And one way to see an example of this is to take the operator that we had on the previous slide. So the operator in little L2 whose entries are all the non-zero integers, and perturb just one of them to, let's say, I, the imaginary unit, okay? So if you do that, then it's relatively easy to show that the numerical range then becomes a horizontal strip in the complex plane of width 1. This, on the other hand, is not perturbed by that rank 1 perturbation that you just made, and so it remains equal to the real axis. So that's in general what happens when you've got a strip. So now, what about the case when your numerical range or its closure is a half plane? What's going to happen now? So I guess you're going to suspect that it's going to be a half plane or a strip or a line, okay? Because a half plane is a union of strips, and strips are unions of lines. So these should be the possibilities, and all three should be possible. Well, I actually know this doesn't happen. It turns out that the essential numerical range is either equal to the closure of the numerical range or it's empty. Okay. So the proofs of these are all elementary. They don't require high-tech stuff. They're all in our paper. So this is really strange. So in this case, where you've got a half plane for the closure of the numerical range, the essential numerical range is either the same or it's nothing at all. If you've got a self-adjoint operator, then I think I mentioned already, it's the extended essential spectrum of T. If T is m sectorial, then it's the extended essential spectrum of the real part of T. And yeah, if T is sectorial, of course, then this will actually be equal to the convex hull of the essential spectrum of the real part of T. And then if T is m sectorial and has compact resolvent, then the essential numerical range turns out to be empty. So the example we had on the previous slide the operator was self-adjoint. It had compact resolvent, but it wasn't sectorial because it wasn't semi-bounded, and so it, this result didn't hold. Okay. So what do we use essential numerical ranges for? So one of the reasons I got interested in essential numerical ranges was because I've been obsessed now for, gosh, far too long for my own good with the problems of spectral pollution and spectral invisibility. And I'd like to tell you what these are. So this is a slide that I've stolen from Sabina's thesis. I think this is the second time in as many weeks that she's seen me stealing one of her slides and giving a talk with it. So this is involves taking a Toeplitz operator and truncating it to finite Toeplitz matrices. And it's been known, at least since the work of Sega, that if you do this, you get the wrong answers. So that the spectrum of the Toeplitz operator is this elegant red curve, self-intersecting in the complex plane. And then the spectrum that you actually see if you cut your Toeplitz operator down to Toeplitz matrices of large size and calculate their eigenvalues is given by these blue dots here. So you can see two phenomena here. First of all, you can see blue dots where there is no red. So spectrum of the truncations converging to points that's not in the spectrum of the operator. That is called spectral pollution. So subsequences of eigenvalues converge to wrong limits. And the second problem that you're seeing didn't really have a name until Matt Colebrook gave it one, and he called it spectral invisibility. So you see here points in the spectrum of the Toeplitz operator that never get any approximating blue knots going anywhere near them. So if you were to just try calculating the spectrum of your Toeplitz operator by using numerical linear algebra, you would assume that all these points out here should be points where the Toeplitz operator would be invertible. Okay, so I should stress here that this is a problem that arises when you insist on approximating spectra with spectra. So you've got an operator, you want to know its spectrum, you truncate it to some other operator, and you calculate the spectrum of that operator. And if you're prepared to do other things like try to calculate pseudospectra, you can go some way towards avoiding some of this. But the way that most people in practice calculate spectra is they calculate spectra with spectra. And so both of these problems remain a real danger. Spectral pollution happens all the time, and I think it's a fairly well understood phenomenon, and I'm going to try to show you how numerical ranges help us to understand it. Spectral invisibility, on the other hand, the fact that there are no blue dots around here, this is poorly understood. So although there's a paper, Schmidt and Spitzer from the 1960s, describing precisely how spectral pollution happens for the Toeplitz case, I think that the explanations that we have at the moment are all very much sui generis. So for each operator for which it happens, we may, if we're lucky, have an explanation, but it doesn't seem to carry over to others. And I'll show you an ordinary differential equation example later on where you get spectral invisibility, just in case you're thinking that it is a pathology of discrete operators. But before we do that, I'd like to tell you about how spectral pollution for compression methods can be understood using essential numerical ranges. So let's suppose we've got some closed operator T on a domain in a Hilbert space, and we take some sequence Pn of finite rank orthogonal projections that converge strongly to the identity. So then we can take T, we can restrict it to the range of P, and then compress back onto the range of P after applying T. So this is essentially now a matrix for all intents and purposes, and the dimension of that matrix is the dimension is the rank of Pn. Okay. So calculating spectrum should be easy, if I can say that without insulting all the many people who have devoted their careers to numerical linear algebra. So in the case of bounded T, this result was proved by Pokrzywa in Krakow in 1979, and then after a very long time, the unbounded case was handled by Sabina and Christiane and myself. So if Tn converges to T in the generalized strong resolvent sense, which is the sense that you would get, is basically the only sense in which you could practically define a concept of convergence here in the setup. If Tn tends to T in GSR sense, then all spectral pollution is contained in the essential numerical range of T. That's the first thing. So the second thing is that every point of the spectrum of T outside the essential numerical range will not be invisible. It will be visible. It will be a cluster point of eigenvalues of these Tn's. Okay, so as long as the point of spectrum that you're trying to find is not in the essential numerical range, that means in particular it better not be a point of essential spectrum. So for example, if it's an isolated eigenvalue finite multiplicity, you're probably okay. Well, as long as it's not in the essential numerical range, of course, then it will be approximated. And then the third result, I need to explain carefully what this means. So the question is, could every point in the essential numerical range that's not in the spectrum turn out to be a point of spectral pollution? So could you choose these Tn's in such a way that every point in the essential numerical range that's not in the spectrum of T be a point of spectral pollution? Now, the answer is, in general, that's too much. Okay, in general, what you can say is that for each such point, you can find a family of projections that will make that point a point of spectral pollution. Okay, but to expect to get all these points as points of spectral pollution with a single family of projections is too much. There are cases where it does happen. So in particular, it doesn't happen for ODEs, but it does happen for PDEs. And there's a paper of Alex Sobolev from 2010, I think, on the Widom conjecture, that if you dig through the theorems there and translate them into the language of here, tells you that for PDEs, in particular for say, Schrödinger operators or even order elliptic PDEs in L2 of RD, this does happen. So you can find a single family of projections that pollutes everywhere in this set. And he even has results on the density of the pollution. Okay, so the density of pollution is not as thick as the density with which you approximate the essential spectrum. Okay, what about PDEs? So here's a fairly gruesome looking slide. So the deal here is that we've got a 2nth order partial differential expression. That's its homogeneous principal symbol there. And this is the lower order stuff that's got some position dependent coefficients. So this is order at most 2n minus 1, and this is order 2n. And let's look at its principal symbol. Let's suppose that this principal symbol P here satisfies this sectoriality condition. So the imaginary part's bounded by a constant plus a multiple of the real part. And then there are some regularity assumptions on these lower order coefficients that I don't want to really dwell on. So we can think of this expression here either in L2 of RD or in some smooth, let's say, smooth bounded domains omega n that are expanding to RD. Okay, and let's say you're working on one of these smooth bounded domains, then you can impose some Dirichlet boundary conditions and get some associated M sectorial Dirichlet operator AN. And then A will be the corresponding operator associated with this in the whole of L2 of RD. So you can prove that AN converges to A. The same is true for the adjoints. This is in generalized strong resolvent sense. And two things happen. First of all, the spectral pollution is all contained in the essential numerical range of A. We'll have to worry now about what that essential numerical range is. Okay. I mean, this is a pretty hairy looking expression. How are we going to calculate its essential numerical range? And secondly, like in the projection case, every point in the spectrum of A that's not in the essential numerical range of A is approximated. So how do we calculate the essential numerical range? Well, that could be tricky, but one case that you can do is, let's suppose that these coefficients, these lower order coefficients, converge to some constants at infinity. Okay, so in that case, you know what the essential spectrum of this is. So the essential spectrum, if you define a polynomial here, so let's define this polynomial. So this is the polynomial that goes with this lower order term. You have psi to the alpha plus beta. You've replaced the coefficients by constants. So this is the polynomial that goes with that lower order term. Here's the polynomial that goes with the principal symbol. This thing here, if I can manage to highlight it, I don't know if you guys can even see the highlighting. Highlighting seems to stop working, sorry. So this set here is the essential spectrum of A, and it turns out, mirabile dictu, that its convex hull is the essential numerical range of A, which is the smallest possible. Now, that's not true in general, but it's true. It does depend on this being a sectorial operator, and it depends on various other things too, which I'm not going into here. But there's an important feature here is that the essential numerical range is invariant under relatively compact perturbations of a type that preserve the structure of the operator. Now, this also explains why dissipative barrier methods leave the spectral pollution behind. So maybe at this stage, well, okay, I'm looking at the time. I'd better not spend too much time talking about this, but I can come back at the end if I've got time. So those of you who were in the Isaac Newton Institute last week will have seen a talk given by Jeff Oval about Anderson localization states. So one thing that you might have, actually, you know what? I'm going to take a risk, and I'm going to try sharing my board. So let's share advanced second camera share. Okay, you can see my board, right? Okay, so let's suppose that you've got some, let's say, a Schrödinger operator minus Laplacian plus G. Let's say in L2 of RD. Okay, so that's your operator T, and let's suppose it's self-adjoint, so V is real valued and it's self-adjoint. And let's suppose that the spectrum for this has some band gap structure. But here's the complex plane, there's the real line, there's the imaginary axis, and we've got some band gap spectral structure. Okay, so and let's suppose that's the bottom of the essential spectrum of P. So this much simpler operator than the one that I just showed you falls within that framework. And so for this operator here, we do actually know that the essential numerical range is the convex hull of the essential spectrum of P. And so it's actually equal to well, equal to half-line. So the essential numerical range covers everything from there on up. Now, suppose you have an eigenvalue. How do you calculate? So The essential numerical range covers the whole of this. So if you approximate this in some way, maybe by domain truncation or maybe by projection, you could get spectral pollution covering over where your eigenvalue is. That's not good news. How will you see the eigenvalue if it's sunk in the sea of spectral pollution? So what you do instead is, instead of T, you look at T plus I chi. So what's chi? Chi, so now this is X. Well, I'm drawing this as if it was one-dimensional. So chi is a smooth cutoff function. Okay, so chi is equal to 1 over a large distance, and then it goes to 0. It may be even compactly supported. Now you know that eigenfunctions of of t, decay exponentially. So the eigenfunction associated with this decays exponentially. Okay, and so if you make R large enough, so you've got, let's say, u is lambda u, and that's your point lambda. Because u decays exponentially, t plus I chi u will be approximately lambda plus I u. So if you look at where the spectrum of this thing is instead of that thing, you will see that it has an eigenvalue that's typically up there, or you'll expect that it has an eigenvalue typically up there. This is now outside the essential numerical range, which has remained down here, because this is a relatively compact perturbation. And so that is removed from the essential spectrum, from the spectral pollution, and you can calculate it. So I really like Jeff Hubel's talk where he showed a use of this for detecting regions of Anderson localization. Okay, let me switch back to my slides. Share screens. Share. Got to get it back into full screen. Okay. I think so this is an example of Brian Davies, where you get spectral invisibility. But I think in view of the time, I'm probably going to skip this and start talking about some of the things that essential numerical ranges can't do. So one of the problems of essential numerical ranges is they are convex. And we've already seen that that might limit their value for dealing with operators that are not sectorial. Okay. And here's an operator that isn't sectorial. So let's take a Lipschitz domain in R3, and let's take this dissipative Maxwell operator. So you see you've got curl here, or I curl on the off diagonals. You've got the usual permeability and permittivity. You can take those equal to 1 if you want to have a bona fide operator and not a linear pencil. Omega here is a spectral parameter, and sigma is the conductivity, which typically is non-negative and compactly supported. Okay, and this has well, it's an operator really. It has an omega independent domain, which for those of you who know about Maxwell is given in terms of these funny H curl spaces. So H curl is a space of functions whose curl is in L2, and H0 curl is a space of functions in H curl whose tangential components vanish on the boundary, very roughly. So remember, this operator acts on vectors. Now you can eliminate one of the fields from this. So you can take the Schur complement of this, eliminate one of the fields, in this case the magnetic field, and you can get this quadratic Schur or quadratic pencil coming out. So you get curl, mu inverse, curl 0, and then you get this funny term at the end, omega epsilon plus I sigma. So where's the spectrum? Where's the essential spectrum? Where's the numerical range? Where's the essential numerical range? And where's the spectral pollution if we truncate the domain? So you have to be careful with this. So let's suppose we're working on a waveguide. So this is meant to be a semi-infinite waveguide in R3. So in the first chunk of the waveguide up to x1 equals 1, we put all the parameters equal to 1. And then after x1 equal to 1, we turn off the conductivity. So this region out here is insulating. So what does the essential spectrum of the Maxwell operator look like in this case? So it turns out in this case, the essential spectrum consists of a point at the origin, 2 points on the negative imaginary axis, and then a part of the real axis. Okay, the real axis with a gap removed around the origin. And this gap from minus lambda 0 to plus lambda 0, well, lambda 0 is the first non-trivial Neumann eigenvalue in the cross-section here. And you'll notice that all the non-imaginary spectrum, well, okay, so I say you notice, you can prove that all the non-imaginary spectrum has imaginary part. This should be a modulus here. So the imaginary part should be between 0 and minus a half. There is also one point where the spectrum has imaginary part. Well, you can see in this case, there's one point where the imaginary part of the spectrum can be smaller, but all the non-imaginary spectrum lies in this set here. So if we go to a picture, the essential numerical range here would be a strip that covers all the way from minus infinity to plus infinity, all the way down to minus I here. The actual spectrum is plotted, and you can see there's a lot less. What happens if we approximate this? So the red essential spectrum, the red is the essential spectrum, the blue is eigenvalues, the yellow is some enclosure that was calculated by a method that I'm not going to tell you about. But the essential numerical range here is going to cover all of this. And so it's not going to guarantee you anything. It's going to basically tell you you could get spectral pollution anywhere, even out here, right? But we know that there is no spectrum out there, actually. And then you do numerics, and the world doesn't end, okay? So I went from there to there, and all that happened really was that these 3 red dots turned blue, and these 2 red lines turned blue as well. So these are actual calculated numbers. So the world didn't end. We didn't get dramatic spectral pollution. So for this case, the essential numerical range is not good enough. And what we have to use is we have to use things called limiting essential spectra, which are studied by Sabina in her thesis. And we can show that if we use domain truncation, then spectral pollution for Maxwell turns out to be purely real, okay? So that's not at all guaranteed by essential numerical range. And so the question is, can we find some other approach that's more generalizable to other problems? And this is really what I'd like to end with by talking about pencil numerical ranges. So pencil numerical ranges I regard as a kind of abstract version of a trick of Moravec's from the 1960s. So if we've got 2 operators A and B, let's define their pencil numerical range with this definition that Christiana doesn't like because it's got a closure here. So the pencil numerical range of the pencil A minus lambda B is a set of all lambda such that 0 is in the closure of the numerical range of the operator A minus lambda B. And then for essential, you just put an E here and an E here, and you can skip the closure because it's already closed. And here's the amazing thing you can prove. You can prove that if you take, so let's suppose that you're looking at T minus lambda I, and you replace it by BT minus lambda B. So you look at these things here, okay? So this is going to be BT minus lambda B in here. So somehow you calculate this pencil numerical range, and now you intersect overall bounded B's. Or you could just intersect overall bounded invertible Bs, what will you get? Well, you'll get a set that lies between the spectrum of T and the approximate point spectrum of T. So for most examples, you'll get precisely the essentials. You'll get precisely the spectrum. And if you do the same with essential numerical ranges, you will get precisely the essential spectrum. Now, of course, doing intersections over all possible bounded operators, you can imagine that that's going to be a bit tricky. It's not going to be practical. But maybe, if you make if you make just a few choices of B, you'll get a superset of the spectrum that's nevertheless small enough to be interesting. So here's an example, which is a toy block operator example for the 1D Stokes problem. So what are you looking at? We've made various cunning choices of B here. T is a 2x2 Stokes operator. I haven't told you what it is. It's got spectrum in the complex plane the way we've done it. And what we're saying here is that the spectrum is contained inside these white regions in the complex plane. So in particular here and here, so these are cases where our dummy Reynolds number is large enough, the spectrum is contained inside these white regions, and these blue regions are guaranteed not to have any spectrum in them at all. Right, and that's really staggering that you get a very, very non-convex enclosure for your spectrum just by using these abstract Moravec tricks with suitably chosen Bs. And then the last thing I'd like to talk about is something that Sabina's working on at the moment. So don't go away and try and do this yourselves, because I can assure you she's well ahead of you. So can you get away with just not having an infinite intersection here, because that's clearly not very practical? Could you get away with having just one or two Bs? And the answer is, for a wide class of self-adjoint operators T, yes, you can. You actually just need one B, and then to intersect the result with the real axis. So what I've done here is I've shown an example of a multiplication operator in L2 of 0, 1, multiplication by a discontinuous symbol. The range of that symbol is these two segments of the real line here at the top of this rectangle. You can see a couple of little red dots there. Okay, so it's just these two little segments of the real line are the spectrum of that discontinuous multiplication operator. You can see there's a gap in the spectrum. And here I've calculated by an unbelievably stupid method one of these guys here for a particular B, essentially random vector method, and you can see that this sees the gap. Okay, it doesn't fill the gap with pollution. So if someone can come up with good ways of calculating these generally quite non-convex sets, then we'll have a brilliant way of avoiding spectral pollution and spectral invisibility. Thank you all very much.
Thank you very much, Marco, for this very interesting talk. I think we can open things up to questions. Delio, I hope you're keeping an eye on YouTube just in case. So if you have any questions or comments, please feel free to unmute yourself or write in the chat. While we're waiting, I will just make the comment that to any German speakers, the W for the numerical range does in fact make sense. It comes from the German, Wertebereich. But this is maybe not so interesting.
Maybe, Marco, can you comment on the spectral invisibility you were just very quickly showing and then skipped?
Right. So I'll go. Do you want to see the sketch for the Toeplitz operator, or will I do the Bryan-Davies one? I think the Bryan-Davies one might be more instructive, actually.
Yes, please go ahead.
Right. So let me stop share and turn on my, go back to camera, share camera. Okay, so let's, come on, share. Okay, so here's Brian Davies' example. I think actually Brian's original example has a 2 here. Okay, so constant coefficient operator, we can obviously calculate what the spectrum of this thing is by Fourier transforms. Spectrum of T. It's going to be the set of all psi squared, let's say plus 2 pi psi, as psi ranges over the real line. So we can draw that. Oops, meant to go through the origin, missed. So that's the spectrum of T. Okay. Now let's suppose that we decide to do domain truncation on this. So if we do domain truncation of this, let's take a truncation R. So we'll do TR is going to be minus d by dx squared plus twice. Actually, let me not do that. Just makes it harder for me to think. So I'll do this in L2 of minus R. And now I need boundary conditions, of course. So my boundary conditions are going to be that elements of the domain of T, R, have to satisfy Dirichlet boundary condition. Okay. Now this operator has purely discrete spectrums. In order to find a spectrum, we need to find the eigenvalues. And to find the eigenvalues, that means we need to solve the equation minus d2 by dx squared of u plus d by dx of u is lambda u. So we need to solve that equation. Okay, so, but this is exactly the same as solving the equation minus d by dx of e to the minus x u by dx is equal to lambda e to the minus x u. Okay, so and this is in L2 of minus r. So the basic, so once you realize that this is what you're looking at, of course, this is a Sturm-Liouville problem with a positive p, positive weight, zero potential, self-adjoint boundary conditions. So that the spectrum of this is just real eigenvalues. Okay, so, and that's true for every R. So as you increase R, you just get lots of eigenvalues piling up densely along the real axis. So you get spectral pollution here, and you never see any of the actual spectrum of the operator at all. And what's going on here is that there are two different operators that have the same formal truncation. There's this operator, this one here, sorry, this one in L2 of R that gives you this equation when you truncate it. But you could also consider the operator associated with that expression in L2 of R with a weight, and that would give you exactly the same truncation. So the information about which Hilbert space you're working in is somehow lost by the truncation process. And then the very strong structural properties of one of the particular operators that happens to have that truncation somehow bullies all the others and forces the spectrum to agree with what it wants. In this case, it has to be real. So there are similar observations about loss of information about the underlying spaces in some of the discrete operator cases, but beyond that, I'm not sure there's a very good understanding of this. So Brian Davies, if you look at his 2002 paper where he introduced this, he doesn't offer very much comment at all, except to say that, well, okay, if we impose periodic boundary conditions instead of Dirichlet, the problem would go away, except that we couldn't prove that it went away if we also added a potential here, even a compactly supported potential. We wouldn't be able to prove then that we gotten rid of this issue.
But okay, if may add the words, I mean, part of the problem, if I get it right, is that if you have periodic boundary conditions, then these two operators, like first and second derivative, they commute, which they don't if you have Dirichlet boundary conditions, right?
Yeah, so that's true. If you've got periodic boundary conditions, then that is true, yes. And yeah, so periodicity is preserved by differentiation, but point values.
So in the periodic boundary conditions, this is where complex eigenvalues start popping up, right? Because the eigenvalues are the sum of the eigenvalues of these two operators.
Yeah. So I mean, this is a good explanation for this operator, but
yeah, sure, of course.
yeah, I'm not sure we have good explanations for other operators. Unlike in the spectral pollution case, where I think we really understand quite well, typically what causes spectral pollution is that your boundary conditions, I mean, physically, your boundary conditions that you've chosen, your artificial boundary conditions, cause waves to be reflected back from the boundary that would otherwise be radiated out to infinity. So spectral pollution in that sense is well understood. There's another way of understanding spectral pollution that I mentioned in Cambridge last week that we're 10 past 4 now, so I probably don't have time to talk about it here. Also, it's not something I've thought about enough. But yeah.
Thank you.
Thank you. Any other questions or comments for Marco?
May I ask?
Yes, Anne-Marie.
Yeah, because you try to kick me out several. But anyway, what about singular operators? So
Sorry,
if the coefficient has singularity, what happens there?
So infinity here is a singular point, and
Yeah, but
if you've got singularities, you can try to do the same analysis. You can try to cut the domain away from the singularity, or you can try to smooth off the singularity, generate a family of regularized operators. Okay. And then you can go through the same sort of analysis. You can ask yourself, do my approximating operators converge in some suitable sense to my limit operator? And then having answered that in the positive, you can then ask, well, does that mean that the essential numerical range captures all the spectral pollution? And at the moment, we can guarantee that in two cases. One is the case where you have some sort of m-sectorial properties. The other case where we can guarantee it is something I haven't spoken about, which is where you can characterize the essential spectrum as somehow arising from Weyl singular sequences that approach where the support of the functions somehow approach the singularity. And there, for those, you can define some special reduced concept, a special different type of essential numerical range. So I've got a paper with Sabina and Christiana, which is hopefully it's going through the production process at Anna-Henri Poincaré at the moment, where we look at things we call Gijlin essential spectrum and essential numerical ranges.
Which essential spectrum?
I'll type it in the chat.
But can you repeat? Gijlin. Yeah.
Yeah. So we even denoted it by the correct Cyrillic character as a subscript in the paper. Yeah, so we can deal with some non-sectorial cases if we understand that the origin of the spectral pollution is waves reflected from faraway artificial boundaries, for example. We can use these Gijlin essential numerical ranges to prove things, to get better enclosures, much smaller enclosures. So we can do, say, Stark operators. We can prove that for classes of Stark operators, the main truncation doesn't pollute. And that was totally impossible before because the Stark operators are not sectorial.
But there's still a lot of work to be done. Okay. So if there are no other questions or comments, I think we might thank Marco again.
Thank you very much.
And thank you to everybody for coming along today. So I think that's where we will be leaving it. The next Lumer lecture, Delio and Katie might be able to comment better than I can, will be in about 2 months.
Yes, so yes.
And it will be working group 3.
Right, that's correct.
So more details will follow soon. Plenty of things happening in the next 2 months this year. So again, thank you to everybody for turning up, and have a great evening.
Bye.
Thank you.
Bye-bye.
Bye. Thank you.
Thank you. Bye.